make sure one thing, that when we mark for the geometry, we only look for the bond pair. Lone pair never ever involves for the geometry. Fine. So that means 4 of these in the plane and 1 coming outside. It will be square pyramidal. Lone pair will never be taken up in geometry because lone pair cannot be seen. It's not an atom. It's free electrons, a pair of free electrons. So it never ever takes up for the geometry formation. So it will be a square and a pyramid coming for the outside fluorine. Right? It will be a square pyramidal. Fine. And the next one is IF7. IF7. Iodine is already there. 7 fluorine atoms. 7 fluorine atoms means I can form a kind of a pentagon over here. But it accommodates only 5 in the plane. 1 fluorine towards the whiteboard, from towards your side, and 1 inside. Clear? What kind of this geometry would be? Pentagon bipyramidal. It's a pentagon in plane. 1 pyramid coming towards you guys from the white blackboard, and 1 going at the back. So it will be pentagonal bipyramidal. Two pyramids, bipyramidal. 1 pyramid, only pyramid. Right? Clear? Okay. Now, next slide, please. After interhalogen compounds, this must be very sure to you guys that interhalogen compounds are more reactive than the respective halogen molecules. So if it is IF7, it must be more reactive with fluorine. Though among a group of halogens, we say that the fluorine is the most reactive, least is iodine, and the reactivity goes down the group. Fine. But if you mark any of the interhalogen compounds, they are going to be more reactive than the halogens. Fine. Clear with this? Okay. Now we move to the noble gas element. This completes up with the halogen elements and the family of halogens. Now we come up with the noble gas, that is the group 18 elements. Next slide, please. Noble gas elements comes up with all your helium, neon, argon, krypton, xenon, radon. All of them are the inert gas elements. The inert term was actually coined because they are really inert, because the octet is complete for them. It is sp2 and sp2 np6. So octet is complete. There is no vacant orbital line, no extra electron putting up. So they are absolutely satisfied, content kind of, you can say, elements. So they need not to share or to react with anything. So that's why they are inert. They are more stable. So if they don't react, their normal molecular state, or you can say that their state, the original state is monatomic. Fine. However, in case of halogens, the more preferred state is the diatomic, because they are incomplete octets, so they form a covalent bond with the other halogen and form a diatomic kind of a species. These do not require any kind of electron, or do not require to take up or give up an electron. So in that very case, they are happy in their own shell and they don't react with anybody, and they are monatomic in earth crust. Now all these gases are chemically unreactive. They form very few compounds. Because of this, they are termed as noble gas. Noble was the term given to those who do not want to react with anybody. This term was taken up very later on. First, they were named as inert gas. because they don't actually interfere in any kind of reaction. They don't react. They don't actually bother for any kind of a system because their octet is complete. Whole of the periodic table actually performs any of the mechanism or any kind of a reaction to complete its octet. Whatever goes on in the whole of the periodic table is to complete its octet and become stable. They are themselves readily having complete octet. So they need not to do anything. That is why they are inert or called as noble. Right? Now their atmospheric abundance in dry air is merely 1% only, by volume of which argon is the major constituent. You must have seen the major constituent of the gases. The maximum is for nitrogen, then for oxygen, and then argon, and then carbon dioxide and rest of the gases comes up. So argon is the most abundant among the inert gases. Radon is obtained as decay product of rayon. Fine. So it's a radioactive element. Next slide, please. Now, atomic and physical properties says that the electronic configuration, except for helium in a group, only helium has S2, 1s2 kind of a configuration. Rest all the inert gases have ns2, np6. Fine. The p orbital is not there for helium. Rest all have S2, P6 kind of a configuration. Only helium has S1S2 kind of a configuration. See, fine. However, ionization energy means the energy required to form the ion. Ion means whether you take up an electron or give up an electron. Fine. So that is not required by these kinds of inert gases because they are full with octet. So if you need to take up an electron, that is ionization energy. The energy required to take up an electron should be very high because that is not a probable condition. They really do not want to actually have a vacant orbital. They are absolutely complete. So taking up an electron will be very difficult. That means will require very lot of energy. Lot of energy will be required if you need to take up an electron. So in that very case, the ionization energy is going to be very high for these substances. Fine. So ionization enthalpy is very high due to stable electronic configuration. However, it decreases down the group. As I told you, that the inertness also decreases down the group. It's maximum for the most lying on the top of the group. As we go down the group, the subshell keeps on increasing. Fine. So inertness also decreases in a way that if you say the central mechanism of the central nucleus is kind of a principal or a monitor who's taking care of the rest of the vacant electrons. As the outermost electron goes farther from the nucleus, there you can say the dominance reduces. So the inertness also reduces as we go down the group. So now they are free to move to the external d electrons, d orbitals. They can move away to d orbitals easily. Fine. So as we go down the group, the inertness also decreases to an extent. Though they all are inert molecules, or you can say the inert gases, but the inertness decreases down the group. Fine. Or you can say other way around, the reactivity increases down the group. Fine. Okay. Next slide, please. Now the atomic radii increases down the group. We all know for all the group, you can say periodic table, the atomic radii increases down the group. However, electron gain enthalpy, due to stable electronic configuration, they have no tendency to accept the electron. As I told you in ionization energy, they do not allow to take up an electron. In electron gain enthalpy, they do not allow to take up an electron also. Neither they want an electron nor they want to give it out an electron. They are absolutely complete. So electron gain enthalpy is also very high for them. Right? So is the ionization energy. Neither they want to take up an electron nor they want to give up an electron. That's why they are complete in their own species and they do not react. So they are monatomic. You will never ever get to hear helium 2, xenon 2, argon 2. You are always listening argon, helium, xenon, neon. Because these are the monoatomic gases. They do not react among themselves also. They don't react with anything. Because of which they form a wonderful application in the world because they can be put up in any of the place where the no reaction is required. Because they won't react at all. So if you want to fill in something where the no reaction kind of a condition is to be performed, you can fill in an inert gas. It won't react with anything. And the volume will also be filled. Right? We'll talk about these in the application part. Next slide. So the physical properties, we say that these are monoatomic. This is very true. Right? Colorless, odorless, because color will get imparted if the electron excitation takes place. Odor will also come up where the electron excitation tasteless. So their existence does not actually come upon with color, odor, or any kind of, you can say, taste. So sparingly soluble in water because of their inertness. Have very low melting and boiling points because the only type of interatomic interaction in these elements is weak dispersion forces. They don't have any interactions among other molecules. So that means there is no breakage of other bonds required. So phase transformation to melting and boiling point takes up at very low temperature. Very less energy is required and they actually melt very easily or boil very easily. If there are intermolecular attractions or interactions coming upon, only then the boiling and the melting point rises. As in the case of HF, I talked about that there is a hydrogen bonding taking up. So because of which more energy is required to break those bonds between two HF molecules. Also the weak hydrogen bonding is to be removed. So to break that molecule, more energy is required, more temperature is to be given. So the boiling point rises. Fine. But here no interaction takes place. So phase transformation can take place at very ease. No extra energy is required. So very low melting and low boiling point actually exist in them. Now, helium has the lowest boiling point, right, of any of the known substance. The boiling point increases down the group because you know that inertness also decreases down the group. So the boiling point will increase down the group. Next slide. Now, chemical properties. Except helium 1s2, all have completely filled octet of S2 P6. Fine. Now, they have high ionization enthalpy and positive electron gain enthalpy. Positive electron gain enthalpy means very high gaining enthalpy. The energy is very high to gain an enthalpy, or an electron. So that means you need lot of energy to make it possible to gain an electron. It's not a very feasible or a spontaneous kind of a reaction. Next slide, please. Okay, so this is a history where it was told that helium, that ionization energy of oxygen was almost identical with that of xenon, because going down the group you get to see that inertness is decreasing. Fine. So xenon coming at very bottom of the group becomes a little reactive, and the ionization energy is somehow comparable to that of oxygen. Kind of a diagonal behavior you get to see in most of the periodic tables groups. Fine. So what you get to see that a xenon reaction was attempted, and what happened? Xenon was made to react with PTF6 in the presence of some room temperature, and this kind of a molecule was formed. And then it was seen that number of xenon molecules could be reacted. Means the xenon was readily available for a lot of reactions under some specific conditions, because though it is reacting, but it's still inert. So some conditions are required, maybe some catalyst, some temperature, some conditions are required. It does not react itself, but some initiation given, it reacts. Right? Next slide. So in that very condition, xenon was reacted with fluorine, and in a mixing of 2:1 or 1:5 or 1:20 at very high temperature, you get to see that it is inert. It does not react under normal conditions. But providing a temperature of 873 or 573 Kelvin, so high temperature, it does react. That means inertness decreases to an extent, but it's still inert. Under normal conditions, it does not react, but providing lot of heat, a lot of energy, it reacts. So it gives you XCF2 in 1:2 ratio, or you can say 1:5 ratio, it gives XCF4 and XCF6, which we have already studied in halogens. Next slide. XCF6 can also be prepared by the interaction of XCF4. What can be done? Like XCF4, if reacted with O2F2, further goes to XCF6, providing oxygen. Right? So properties are like XeF2, XeF4 and XeF6 are colorless crystalline solids and sublime readily at room temperature. 298 is the room temperature. Fine. 298 is 25 degrees Celsius. 298 Kelvin. So they are very powerful fluorinating agents. Fluorinating agents, they are very much fluorinating agents. What are fluorinating agents? Fluorination is required many a times. Your toothpaste contains a lot of fluorinating agents, which strengthens your gums. Calcium and fluorine is very much required for the human body also. Right? Next slide. Now, these are the reactions where XeF2 in presence of water gives xenon back again along with HF and oxygen. Because hydrolysis of XeF2 provides you back again Xe. So, Xe in xenon in presence of fluorine and some high temperature forms a complex XeF4, XeF2 or XeF6 provided with the temperature and the composition concentration variations, right? But they can be reverted back if these complexes are hydrolyzed, dissolved in water. You get xenon back again. Get to see XeF2 giving you Xe on hydrolysis. So is with the case of XeF4 on hydrolysis gives you Xe, and XeF6 also gives you. But the condition here is it gives you not only xenon but an oxide of xenon. Fine? Because higher is the oxidation state, more difficult it is to get you back the xenon. Right? Next slide, please. Now, XeF2, xenon fluoride reacts with fluoride ion acceptors to form cationic species and fluoride ion donor to form fluoroanions. What happens with these kinds of reactions? A kind of, you can say, cationic anionic complexes are being formed with PF5, SBF5 and MF5. With fluorine acceptors, it gives you different complexes. Fine? Cationic and anionic complexes are being formed. Next slide. Now these are the structures of different xenon fluorides. You get to see that this is XeF2, 2F molecules. Now this time Xe has 8 electron in its outermost shell, or you can say valency is 8, not the outermost shell. Let's say valency is 8. So it should be accommodating 8 electrons outside. One towards fluorine here, one towards fluorine, and fluorine must be having accommodating one more from itself. So that means 2 for xenon for the bond pairs, remaining with 6, forming 3 lone pairs. 1, 2, 3. What geometry it is going to be? Linear. Fine. And the kind of hybridization it is going to be is sp3d. Right? Because p orbital will be requiring 2 of its electrons to move. Okay, when it comes to your square planar, 4 for fluorines, remaining are the 4 electrons forming 2 lone pairs. It will be this way. Now lone pairs do not get added up or associated in the geometry. We never count lone pair for the geometry formation. We only look for the bond pair for the geometry. Fine. So the geometry becomes square planar. Clear? Now the next one is XeF6. Though XeF6 is very easy to be formed, where the 4, you can say, planar structures are in the plane, one down and one above should be there, forming an octahedral geometry. But accommodating 6 fluorine molecules leaves behind 2 electrons, forming one lone pair. So where that lone pair would have accommodated. Fine. So it actually kind of a distorted octahedral is formed. That fluorine gets steric hindrance from this lone pair, and it gets a kind of shift from the 90-degree angle. It gets shifted a bit, and because of which it gets a distorted octahedral structure. Fine. Next slide, please. However, the structure of XeO3 you can get to see, because you know that XeF4 when reacted with water provides you xenon, but XeF6 reacting with water does not provide xenon, rather it provides XeO3. Fine. So XeO3 is this kind of a structure because oxygen valency is 2. So every time it requires 2 electrons of xenon, each oxygen requires 2 electrons of xenon for the bond pair forming with each oxygen. So it will be 1, 2, 3, 4, 5, 6. Still xenon is left with one lone pair, or you can say 2 electrons. So that means this kind of a geometry. Fine. So this is a pyramidal kind of a structure. Clear? Next slide, please. Okay. So XeF6 in water, many a times partial hydrolysis of XeF6 also takes place. Partial hydrolysis means that not in excess of water, little amount of water, the hydrolysis does not lead to XeO3 kind of a formation. It also gives you XeOF4. So always remember, in your MCQ, they may ask you that what goes when XeF6 reacts with water. If it is the complete hydrolysis, XeO3 will be formed. But if it is partial, partial means little amount of water is given, displacement of one oxygen will take place for 2 fluorine. Because you know, fluorine forms one bond with xenon and oxygen forms 2. So you can say take up of one oxygen will give up 2 fluorine molecules. So it will form XeF4. Again with little amount of water, because water, what it provides oxygen. Again another molecule of oxygen is taking up at the expense of 2 fluorine. So it will be XeO2F2. You need not to mug up, these reactions are very easy. Another partial, this you can say hydrolysis would lead you to these at the expense of these 2 fluorine. You will further get one oxygen. So it will be XeFO3. So these are the step-by-step hydrolysis, or you may say the partial hydrolysis of XeF6, which take up at the expense of fluorine. Going, you can say taking up of one oxygen will give up 2 fluorine molecules. Just remember that. So step by step, you will get abduction of oxygen. This is a mechanism, you can say, for the hydrolysis of XeF6, how XeO3 forms. Right? So each fluorine gets off with one oxygen. 2 fluorine goes off with one oxygen. Fine. So XeOF4 is a colorless volatile liquid and has a square pyramidal molecule, because 4 will be in plane. Fine. 1 will be above oxygen with 2 bonds. There is no need of any of the lone pairs, because 2 bonds, or will there be? Tell me. XeOF4. 4 in plane. 2 oxygen with the molecule, oxygen molecule. How many is left? 2 electrons are left. 1 lone pair, that is at the bottom. But the geometry won't count for the lone pair. So it will be square pyramidal. Fine. So square pyramidal is the geometry. Many a time geometry may be asked in your MCQ. So you must be very clear that what kind of geometry should be formed with the periodic groups. So for that, you need to remember the valency. Each element should actually satisfy its valency. Valency does not mean the outermost orbital. Valency means S and P in total, how many electrons constituted. Fine. Like for halogens, it was 7. For inert gases, it's 8. So always make sure that it comes up to be the same. For bond pair, it accommodates only 1 electron. For lone pair, 2 electrons should come up. Fine. Next slide. Now this is the geometry we were talking about. F4, 2 for oxygen, in total 6 bond pairs and 1 left out, remaining lone pair. So the geometry would be square pyramidal. You can see here the molecular modeling structure is there. Fine. These are fluorines, xenon, oxygen. What happens with the XeF2O, 2, F and oxygen? Oxygen requires 2 each of them. 1, 2, 3, 4, 5 and 6. 1 lone pair is again left. So the lone pair comes up above, and this is a kind of a seesaw shape. It is not tetrahedral. It is a seesaw shape. Right? Next slide, please. Now, let's talk about the uses of noble gases, because they do not have enough of the application in terms of the chemical reactivity, because these are inert. So it's only xenon which forms some, you can say, reactions are taken up by xenon, and hence there comes some structures for those reactions we have talked about. Basically, we need to talk about the uses of the halogens. Sorry, inert elements. So inert element uses comes up with helium because it is non-inflammable and light gas. Light because it is smaller in size also. So it's being used in filling up of the balloon